This type of problem is a real classic in ordinary differential equations. It's known as the well-stirred tank problem. So let me read it to you. A 200-gallon tank contains 5 pounds of salt to start with. Water containing 1 pound of salt per 8 gallons enters in at 2 gallons per minute. The well-stirred tank is drained at the same rate, 2 gallons per minute. After how many minutes will there be 20 gallons of salt? Okay, so now ultimately, let's look at the thing about this problem. It starts off with 5 pounds. If this just runs forever, you know, water's coming in, water's draining out, it's being stirred, but a higher concentration is going into the tank, so the salt is building up in there. And if you look at 200 gallons at a concentration of 1 pound per 8 gallon, 1 pound per 8 gallons, the gallons units cancel. That tells you how many pounds we expect eventually to have in this tank. I mean, it'll just keep on growing until it reaches 25 pounds. So at some point down the road, we expect there to be very close to 25 pounds. In fact, it's going to be asymptotic. We're starting here at 5 pounds, and as time goes to infinity, the amount of salt in the tank is going to increase asymptotically, so that the limit as time goes to infinity will be 25 pounds. Somewhere in here is 20 pounds, and we want to figure out how much time that takes. So this is sort of, I think you'll agree, this is sort of what we expect to see. That we have a low concentration of salt, we're pouring in a higher concentration of salt. In the beginning, it's going to start really increasing the concentration, but as it gets closer and closer to 25 pounds, that there'll be a less and less of an increase. It'll approach asymptotically. So I hope this estimate of what we think is going to happen makes sense to you. So let's see what happens here. And I haven't worked this problem, so I don't know what the outcome is. I like flying by the seat of my pants sometimes and doing these videos, or in class. More fun for me. Alright, so here we've got this tank, and you'll find out that I'm not a great artist, but contains 200 gallons, and pouring into the tank is water is pouring in at 2 gallons per minute, and the concentration is 1 pound per 8 gallons. Now, if we let y at t equal to the pounds of salt in the tank, then what can we say about the salt going out? Okay, well, the water is pouring out at 2 gallons per minute, but the amount of salt pouring out is y pounds per 200 gallons. So for example, at the instant this problem starts, we have 5 pounds dissolved in 200 gallons. And so the concentration of the salt is initially 5 pounds divided by 200, 1 over 40 pounds per gallon. But that's going to change because the amount of salt in the tank is constantly changing. Now, here we go. Here's a good point to make. You know, why do we need calculus? We use calculus to solve problems in which things are changing continuously. And differential equations handle those situations where there's continuous change. And so by calling it the well-stirred tank problem, the amount of salt is constantly changing in the tank. And so we account for this constant change with derivatives. Alright, so in differential equations. So to kind of map out this problem, you might say, well, okay, the rate of change, the rate at which the salt is changing, rate let me write that a little more legibly. The rate of change in the salt would equal to what? Well, it's the salt coming in minus the salt going out. So salt comes in, salt comes out constantly. That's providing a rate of change in the salt concentration. Okay, so let's translate this into a differential equation. And for that I need to do some erasing. By the way, these well-stirred tank problems do appear in your textbook. I forgot what chapter, but I think it might be chapter 3. Yep. Problems leading to first order equations is chapter 3. So I'm going to, if you're wondering, I'm going to cover chapter 2 and occasionally work problems from chapter 3 as irrelevant. And so I like to kind of mix it up a little bit there. But the book divides into just differential equations without applications and then a whole chapter of applications. And that's the way the book divides it. I'll probably mix it up a little bit more that way. Alright, so the rate of change in the salt is the rate at which the pounds of salt is changing with respect to time. That's the derivative. That's the derivative of y with respect to time. The rate of change in salt with respect to time is dy dt, or y prime, if you prefer to call it y prime. Alright, how much salt is going in? Well, it's going in at 1 pound per 8 gallons. That's the concentration, and the rate of the water flow is 2 gallons per minute. So what happens here is the gallon units cancel, and I get, for this part, 2 over 8, 1/4 pounds per minute. But then it's flowing out at what rate? Well, we have y pounds per 200 gallons. So y pounds per 200 gallons. And the rate is still 2 gallons per minute. 2 gallons per minute. And so when I simplify this, the gallons cancel again. And the 2 cancels the 200, leaving 100 down below. So this is y over 100. And it's also pounds per minute. Alright, so when you think of the units here, this is pounds, dy is measured in pounds, dt, t is measured in minutes. So we have pounds divided by minutes, pounds over minutes, pounds over minutes. The units agree. If those units didn't agree, then the equation would be wrong. It would be a non-starter. We wouldn't be able to solve anything. So the units have to agree and make sense in order to solve this. Okay, well, let's solve the differential equations. So I'm going to erase all this stuff. And now we have dy over dt equals to 1/4 minus y over 100.